Hi everyone! Today's lecture is related to the discrete time Fourier transform. Uh, Let me tell you that the Fourier transform is an incredible important signal processing technique in time series data analysis. The backbone of the Fourier transform is the dot product. Do you remember how to compute the dot product from previous lecture? The Fourier transform works by computing the dot product between the signal, let's say a biosignal that you are acquiring from sensors, and sine waves of different frequencies. These are the kernels. So let's begin with making waves. You already know how to compute the dot product. It's time to learn about creating sine waves now. Sine waves can be represented mathematically using the following formula. Okay, so in which A is the amplitude of the sine wave, F is just the frequency of the signal, T is just the time, and theta is just the phase angle offset that you will see here. For instance, the phase angle is just a number that represents how many degrees a sine wave is out of phase with respect to a reference. Let's say the reference is just 0, or it could be another sine wave. So in this case, the phase angle is represented like how many degrees are is out of phase the signal, the blue signal, with respect to the red one. Now let me tell you that how to compute the discrete time Fourier transform. The idea behind this is fairly simple. First, you need to create a sine wave. Okay, a sine wave at, let's say, with a frequency, and this will be the original data. Let's say that this example, you need to approximate the original signal, which is a square wave, and the first step corresponds to creating a sine wave and then compute the dot product between the sine wave and the time series data. So in this case, you will obtain a dot product between both signals, and then the process continues by creating another sine wave with different frequency. So again, you will need to compute the dot product between both signals, and you will have a different response. Continue by generating more sine waves, and the number of sine waves you create is determined by the number of data points in the time series data. So you will obtain at each iteration, you will obtain some different, let's say, forms of these sine waves, and you will try to approximate to the original signal. My original signal in this example is just a square wave. So let me give you a general pseudocode that will perform a discrete time Fourier transform, let's say of random data for now. So let's begin with n equals to 10, which is the length of the sequence of the data. Data corresponds to the set of random numbers from 1 to n, and we need to initialize the Fourier coefficients. Fourier coefficients will be an array filled out with zeros of length data, and let me describe the time array. Time starts at 0 to n minus 1 because 0 counts, and divided by n normalizes to 1, so the time will be 0 to 1, but of course with length n minus 1. And then you will need to create a for loop because you will try to generate sine waves at each iteration. Remember that the number of sine waves that you will create is determined by the number of data points in the time series data. So first you need to create a sine wave. How to create a sine wave? Well, let me give you an example of this. Notice that the equation for the sine wave looks different here. You can still see the 2 pi f time part, but there's no sine function. And instead, there's an exponential and there's a minus I. So this makes a complex sine wave. For now, just keep in mind that this is a sine wave too. You can also notice that the frequency of the sine wave is defined by 1 less than the looping index, so fi minus 1, whereas you might expect that to be defined by fi. The sine wave at each iteration corresponds to a frequency one step lower than the iteration. Notice that. Thus, the first iteration of the loop produces a sine wave of zero frequency. This is called the DC component, where DC stands for direct current. Then you need to compute the dot product between sine wave and the data. So the dot product computes the mapping between two vectors. So this will be the dot product between the sine wave and the data. And that will be all. This is the general algorithm for computing the discrete time Fourier transform of data. So the formula for the discrete time Fourier transform looks like this. Let's say that discrete Fourier transform of variable x at frequency f is just this, the sum of the dot product between the sine wave and the data. So n refers to the number of data points in vector x, and capital XF is the Fourier coefficient of time series variable x at frequency f. So imagine that you will have a time series data or time series signal, which is, let's say, a biosignal that you are acquiring from sensors, let's say brain signals, muscles, electrical signals, or something like that. And the data, if you plot the data, you will get amplitude, which will be voltage, with respect to time. So this will be vector xk. If you compute the Fourier transform, you're creating a dot product between both, let's say, from different signals at different frequencies. Then the result will give you a frequency domain response. This is a time domain response, and this is a frequency domain response. So you will obtain, after computing the Fourier transform, you will obtain, let's say now, power with respect to frequency. And you will see that which frequencies have more power than with respect to another one. Let's say that this signal corresponds, let's say that the frequencies that characterizes this signal corresponds to this frequency and these frequencies. Okay, so let me give you a final example of this. If you create or if you compute the Fourier transform of this signal, you will obtain something like this, that you will see that you have more power here at frequency 1 Hz probably, and the rest of the frequencies are probably equals to 0. So I might say that this signal corresponds to a 1 Hz signal. But if you compute now the Fourier transform from this for this signal, you will obtain probably higher frequencies. So I might say that probably this signal corresponds to a 5 Hz signal, because at 5 Hz I can see that there is enough power with respect to the rest of the frequencies. And finally, probably this signal corresponds to the sum of the first and the second one. So if you sum of this, you will obtain, let's say, a signal with different frequencies So let me compute the Fourier transform from this for this signal, and now you will see that there's enough power at 5 Hertz, but of course you will obtain some less power but greater than 0 at 1 Hertz. It would tell you that the frequencies that characterizes the signal corresponds to these two frequencies. This will give you an idea that how many frequencies you will have in a signal. So when you are acquiring biosignals, you will need to identify which frequencies that you have. Imagine that this will have probably you will have a noisy signal, and you will need to describe how many frequencies you will have in that kind of signals. Well, that's all for now. Thank you, guys.